Hello, everyone. We'll go ahead and get started with our webinar. Today we are going to take a deep dive into CICPs for this topic for the month. We will be recording this session as we always do, and all of those in attendance today will get the recording link as well as the PDF of the presentation. If you have any questions, feel free to use the chat box and I'll take care of addressing those at the end of the presentation. And with that, I'll go ahead and get started and go off camera a little bit here. All right, so we will talk about the CICPs, and they are part of, certainly they are a pigment on the inorganic side, so you can follow this trail of how they are. They are synthetic, and they do have a structure towards them. And it is this structure that creates the individual color index for each of the pigments that we'll discuss. That's the important part of CICPs is the actual structure itself. A little deeper dive into the inorganic tree of areas. So talked about them being structured. The two main types of structures are the spinels and the rutiles. So you can see some of the more important types of CICPs in these two categories. A lot of these you'll recognize that are being used very much in today's areas, application areas. For those that are more visual, like myself, I just wanted to give you a feel for how CICPs fall into the full inorganic space. So we have the mixed metal oxides, which is the overall category, and then the CICPs are a subset of mixed metal oxides. And really, as I mentioned, the general category is mixed metal oxides, and the key there is that there are two or more metals that are in the oxide crystal. As an example, an iron oxide that we all know and love does only have the one metal. So mixed metal oxides are distinguished by having more than one. And the CICP is a subset of mixed metal oxides because it's it designates that they are colors. So there's more colorful options, if you will, in this subset of mixed metal oxides that make up the CICP area. But again, the key thing is the word colored in the name. How they're made. This is a continuous process that takes the metals and oxides and brings them together in a calcination process, which is really a very strong heating in an air environment of these blends of metal oxides. The temperatures are very high. They start out on the low end, if you could call it low, at 650 degrees C, and they ramp up to 1300 degrees C. And different things happen at different times in the temperature zones in this tube that is the calcination tube. At the lower temperatures, this is where the decomposition to the metal oxides occur. At the higher temperatures from the middle to the end of the tube, this is where the oxide metals become reactive, and then they can combine together into the new crystal structure. At the higher temperatures, this is where they rearrange, as I mentioned, and that end rearrangement to create the crystal is determined by three things: which metals are present, the oxygen to metal ratio, and the temperature at which the crystal is created. And so Those are very key and very precise to achieve that final crystal structure that you're trying to create. Once the crystal is created, the process are very similar to other organic pigments. There's some milling that goes on to get to the final particle size needed. It can be washed and then blended in with to create the final lot of material. So there's always pros and cons to every type of pigment class. Certainly CICPs do have their own pros and cons. The number of pros are these are extremely weather fast and chemical resistance. They have, because they're created at such a high temperature, they are have the highest heat resistance available to the formulator. They have low oil absorption, so you can achieve high loading levels and thus high hiding power. They are good to have good dispersibility. However, they are hard particles, so they're not really a good candidates for just dissolver types of dispersion processes. On the plastic sides, they typically have no or very low warping and migration, and they also have excellent fineness when they're ground in a liquid environment. Of course, with every pro, there's also cons. Because they're inorganic pigments, they do have a low tinting strength and lower chroma versus their organic counterparts. But this is where the organics come in handy. They mixing them with the CICPs raises that strength and increases that chroma availability with a combination. So applications, it's really, these are all about the durability that they offer to your formulation and application. They're used in all types of application areas in the liquid coatings area, especially for exterior and very rugged environments. They are used in plastics, certainly in siding, window frames, construction materials. They show up in bricks and plaster and concrete types of things. Glass and ceramics, very high temperature application area. That's where these are very good for that because they are created at such a high temperature. Periodic table, for those of us who are a little geeky here, gives you an idea of how these are created. The ones that I have in a red circle, those elements are the responsible for the primary color. And then the ones in the blue triangles are used for two things. They balance the charge in the final crystal structure, but they also help to modify the hue of the final product in there. So you'll see some examples a little later on how you can manipulate the formulation and to achieve a different hue. As I mentioned, the structure is determined by the oxygen to metal ratio. There's two dominant structures in the class: the rutile and the spinel. They dominate the volume of CICPs in the industry. The third is the hermatite. They're much less common, but they're still present. Just to give you an idea of when you're seeing a name or a CI color index name, give you an idea of what the structure is. So in this chart, these are just some common CICPs that are used in industry. And you can get a little bit of a feel for the type of structure by the name of it. So chromites tend to be in the spinel class. Titanates tend to be in the rutile. Illuminates also in the spinel, and ferrates in there. So it gives you a feel for what kind of a structure it is based on the name as well. So I talked about the oxygen to metal ratio. This is where it's key in the manufacture of these particular pigments. So rutiles, they always will have an oxygen to metal ratio of 2. And in this particular case, the crystal is connected by 6 oxygen ions in this octahedral crystal shape in there. So it's very specific in that crystal structure to be able to create those color indexes with this type of ratio. This is the largest family of CICPs. It's about, and they contain a large amount of TiO2 in those areas. They color ranges are typically very light yellow to darker browns. Even though they have a large portion of TiO2 in the crystal itself, it does not carry the same photodegradation properties of TiO2 individually. So there's a lot of potential for property improvement of your formulation by swapping out TiO2 and a CICP to get those extra durability properties that you might be looking for. The spinel grouping of CICPs have the oxygen to metal ratio of a 1.3. In this case, they will contain metal ions of different oxidation states. Typically, a +2 and a +3 are within that structure. And in some cases, there will be 2 distinct environments for these ions to orient themselves, the octahedral and tetrahedral, depending on the oxidation state of the metal itself. And then lastly, the third smaller grouping of CICPs are the hematite, with an oxygen to metal ratio of a 1.5. And these are also based off of trivalent metals in an octahedral shape of crystal. So those are the key to creating the actual chemistry that we're trying to achieve through this calcination process. So as far as the groupings, then there's the kind of the subgroupings with respect to the titanates, aluminates, and chromates. The titanates are the biggest volume of CICPs that are out there. Within titanates, there's both rutile and spinel grades. The rutiles are the light yellows to browns. The spinel grades are greens to browns. Aluminates are in the spinel crystal structure category. You'll know these more about the cobalts, cobalt blues, cobalt greens. Typically, these are the cobalt is the coloring oxide. And these range from blue to teal and green in that space. And then the last grouping is the chromites and ferrites. These are based off of chrome and or iron oxide as the base metal in here. So the 3 main groups that are used under the CICP category. So if we dive into the actual types of color indexes within these categories, the first one is the pigment yellow 53. This is a workhorse inorganic pigment in especially in plastics and in coatings area. It's the second largest volume CICP available. These all have the same types of properties. So there's no photocatalytic behavior. And they have the great light and weather fastness, good hiding power, high heat resistance. These are all the same for each of the categories. So you'll see this over and over again as I go through them. Um, we can vary the color, as I mentioned in an earlier slide with the periodic table. They can be optimized, the tinting strength can be optimized by particle size selection and distribution. And then the shade can be shifted by changing the ratios of the metals within the crystal structure. Give you a feel for that shift in hue. This is an example of color space available for a number of pigment yellow 53s. So you can see that there are mostly in the green side of the color space, with some a little bit to the redder side as well. So options always are available to be able to meet your needs. And those are achieved by that adjustment in the metal ion complex. So from a product perspective, primarily these are found in powder form, although there are some in liquid form as well, to be able to be able to give the liquid area some support. And so, but these are also great tools from a color perspective in here. And so I provided you actually this month's color of the month utilizes both CICPs and an organic blue as well to create this lovely deep blue color, solid color. Pigment Brown 24, this is going to be the highest volume of CICPs. It's well known in the industries as that workhorse in there. It carries a very nice color, a very light tan, if you will, in there. It has all the same properties as a CICP would, so that the areas can be covered with respect to all your needs. And again, same idea here, varying the strength and opacity by the particle size and distribution, varying the hue by the change in that ratio of metal content in there. Give you a feel for where products can sit in the color space area. So there's a number of products here. They range with a nearly a 10 unit difference in the red to green value, as well as in the L value as far as lightness is concerned, to be able to see that space and the options available, all by shifting those parameters to get different hues. As I mentioned, strength and hiding is by particle size, and then of course incorporating different coloring ions or shifting the ratio changes that hue. Here's an example of Brown 24 during. Really, this data is actually during a development of a product here, where we started that effect of shifting those colorants in here. So you can see in this example that we were able to shift the red to green by 2.5 units. Just by shifting that composition a little bit before we selected on where we wanted to be for the product. As I mentioned earlier, this is the highest volume of CICP, and this is an example of that. There's a lot of products available, a lot of color spaces that are filled. In this particular case, we also have some liquid versions as well to support the coatings area for in that space. So a lot of options to be able to meet your needs. Pigment Yellow 164. This is the third in the rutile area. This is a lovely dark brown color, all the same properties in here as the other CICP, so I won't go too far into that one, but wanted you to be able to see the color here. From a product perspective, there's one available from the legacy Sudarshan area, and we used that one to create last year's June color of the month with this pigment yellow 164 and a gold mica to be able to get this nice walnut shade of color. To give you a feel for going down the how to change the color via the metal ion, here's that example that I told you. So we talked about the yellow 53, brown 24, yellow 164, but when you change out from nickel to chromium to manganese, you see how the shade shifts from a yellow to tan to brown with respect to that. And just so we can match that up to the periodic table, you can see how the shading component of the antimony is equal to each of each of those color indexes, and the primary metal ion is in the dark, the bold red circles there, so you can see how that shifts. Shifting to spinels is pigment yellow 119. This tends to be a little bit to the yellow side, but also a little bit to the reddish side, more of a buff or tan color. This is also has the same type of thing. This is very useful with respect to combining it with organic pigments. This allows to get to more natural greens and brighter reds and chocolate browns with a good hiding and good cost position in there. So consider this as an area to be able to get to those. Again, I call them natural colors, but it's a good combination in there. Coloristically, it's a lovely color to be able to do it. With this product, we've done a number of color formulations using it as a primary colorant as well as a sort of a balancing colorant for hiding efforts as well. So in both of these cases, they are different levels, but also are there for that good hiding and good heat reduction and base for those organic pigments and micas. Pigment Black 28 is again another one of those workhorses in the industry. It's also of the spinel lattice. This is typically more bluish black in shade of color. It has all the same properties in here. I always have to say it's not carbon black. It doesn't have the color, the jetness of a carbon black, but it has a lot of other positive properties that carbon black does not have. From a shade perspective, from both brown and black area, you can see where they fall with respect to the blueness aspect of it. They typically are to the more blue side and available. From a product perspective, there are several available to be able to do that. Again, I use it as a very good base for color instead of using carbon black, because I want to be able to provide colors that are heat stable, that are NIR reflective for LiDAR type of applications and recycling kind of a thing. So in this particular case, we see some formulations that are using the Black 28 as a base to support both micas and other organic pigments as well in here. We wouldn't normally think about the combination of a inorganic pigment and micas, but it works out very, very well. especially like in the silver area of the silver fog, where you can start to approach the aluminum color positioning with the combination of black 28 and a silver mica, to be able to get that color space and effect, with respect to the CICPs. Blue 28, cobalt blue, as everybody knows them well. These are the red shade blue in color. Again, same properties, technical properties as all CICPs. And this is also something where we've played around and can really change the level of, or the hue, I should say, of based on the metals and the ratios that are in there. To give you a reference point, I put in this chart blue 15-1, the organic blue, just as a color reference in here to give a feel for where blue 28 sits from a color perspective. So in this particular case, the Legacy Sudarshan product has the same redness value as a blue 15-1, but then it will offer more opacity if that's a property that's desired, but it is also more blue in there. So if I zoom into just the blue 28s, and you can see how we were able to evaluate shift in the metals to get to shift the hue and where we wanted to be. So we can move that redness to greenness quite significantly with respect to how we make the ratio of the metals in the crystal. From a product's perspective, this shows up in a number of areas with respect to liquids as well as powder forms. Blue 36, another cobalt green. This is more towards the green side of the blue space, or some people might call it teal in there. So there's a lot of options in this aspect of it. From a product perspective, this is not as popular versus the blue 28, but there are products available to be able to hit those more unique spaces. Green 50 is the cobalt green, as you might know it as. This is a more of a brighter green shade, more to the yellow side in green space. And from a product perspective, again, these are available both in powder and liquid form to be able to meet your needs. And it's usually a combination of blue 50, blue 28, and green 50 that are used instead of the blue 36 to get to those more teal spaces, primarily because just the volumes of the blue 28 and the green 50 tend to be more, so that they already have them available. Green 26, this is a combination of cobalt and chromium. This move shifts in color to the blue side of the green space. Give you a feel for where the in color space where the blues and greens fit, so that you get a better idea of choices that you have. So we've got the blue 28s over here, the blue 26, or I'm sorry, the blue 36 here, and then a couple of green 50s over here to show you how the color shifts with those crystals. Likewise, as I mentioned in the earlier slide with the rutiles, here you can see swapping out the metal ion shifts the color space. So in the green space, moving from titanium to chromium, with the green 50 to the green 26, shifts from yellow to blue. And on the blue side, when we swap out one of the aluminums for a chromium, we move from the red space to the green space for blue. And if I bring back my my periodic table here, the main area is the cobalt. It shows up in all of those. And then in the green 26, the green 26, we introduce a second metal oxide, primary oxide to get that blue color. And then we have the aluminum and the titanium for modifying the hue there. So you get a feel for what those metals do. So now that we've gone through what are CICPs, now we'll talk about how to use them and how to take advantage of all the properties that they have. One of the primary ones is to help with solar reflectance. Obviously, we all know how the sun impacts all of our application areas, whether it be heat or color stability, safety from a surface heat perspective. There are a number of things that that the sun can do to your customer's end application that we as formulators and pigment suppliers need to address up front in the formulation so that your end customers can be you can get the best formulation for your customer to be able to meet as many of those needs as possible in there. So the CICPs are great for doing these. They can help to reduce the energy demand for cooling on the inside. So your air conditioning in your car, the fuel usage in a plane. Think lightweighting with the hiding impact with respect to the coating. The damage or deformation of plastics can be minimized or eliminated by using more of the CICPs. So think siding on the vinyl siding on your houses in there. That's one of the properties that the CICPs bring to that application area. I talked about surface temperatures of all kinds of articles. So last thing you want to do is go and touch something and burn your hand or sit on something. So think car seats, leather car seats in the sun. How many times have we burned our legs by sitting on hot car seats or a park bench in an amusement park? Those are the kinds of things that if thought of up front can help with those types of properties. So the problem area is in the near IR, which makes up about 58% of the sun's irradiance in there. Color space that we see in the visible space is what we see with our eyes in there, but we have to deal with that 58% from a technical property perspective. It's measured via this type of a machinery. There's many out there that do the same type of thing, but it's really specifically looking at these wavelength ranges to be able to get that total solar reflectance percentage. And there we're specifically looking at the 700 to 1500 nanometer spaces for that one. This is an example of a pigment yellow 53 that has 74% solar reflectance value to it in there. So it gives that nice light yellow color, great hiding, but it also reflects 74% of the solar energy coming in. The best pigment for this particular property is going to be TiO2. It's near 100% in there, but not everything can be white, of course. Just to give you a feel for the total solar reflectance of different color indexes within the CICP category, you can see that a variety of levels of reflectance are in there. And you can see how you can work them into your formulations to be able to take advantage of that particular property. The second example is creating more cost-effective formulations. And the cost effectiveness comes in a couple of ways. And that could be you as a formulator taking advantage of that by taking advantage of the hiding impact of CICP so that your P2B in your formulation is lower. So you as a consumer of the pigment can take advantage of that. Or you could choose to pass that along to your end customer by providing them a formulation that has a higher hiding powder, so they would use less material in their application and get the same type of hide. Here, a great example would be in the aerospace industry for lightweighting. The coating on the airplane, if you can reduce that thickness of the coating, even very little, they have huge calculations that can correlate to the amount of fuel that they could reduce by just lightweighting that coating example. So different options depending on what the need is. And here's some RIL colors examples where I show the organic versus the total inorganic, as well as the organic types of costing for those types of formulations. The third example is enhancing chroma as well as hiding power in combination with organic pigments. So in this case, we are using the pigment brown 24 in combination with a couple of red pigments here, red 112 and red 254. So on the right hand side is the TiO2 formulation, the same exact formulation using swapping out for the pigment brown 24. We see chroma enhancement, and then there's also going to be a hiding power advantage as well. Now, I will mention that in addition to these particular properties, you'll also have a weatherability perspective improvement as well, especially with the red 254, which is a known organic pigment that has that TiO2 susceptibility for photodegradation. So swapping that out will get that property improved as well. In the yellow space, here we are using the pigment yellow 53, swapping out for the TiO2. So in each case here, we see an improvement in that chroma with the additional hiding power coming from the CICP. And once again, there's also that weathering improvement, especially with the orange 36, that is very susceptible to the TiO2. As I mentioned with the weathering, the fourth example is weatherability and higher hiding power. So here we created a few examples where we swapped out, we reformulated, I should say, the color, doing a organic based versus a CICP based in here. And in this particular color, the RAL 1003 is primarily formulated with the 154 and the yellow 139. It's the yellow 139 that has the issues with TiO2, as well as issues with iron oxide being sensitive to that particular one. So that's the colorant that we want to be able to use if needed, but be able to create a better weathering environment. So changing things around and reformulating it, and essentially the goal here is I want to remove the TiO2 primarily, and in this case I also wanted to remove the iron oxide if possible for that. So in this case we were able to get that similar color space with brown 24 and yellow 53. So we got the space, but we also got the much more hiding. So as I mentioned earlier, the choice is yours, whether you want to create a lower P2B formulation or offer that to your end customer with a lower film build product. And then on the orange side, this yellow orange side, same idea. In this particular case, there are three key pigments in here that are very sensitive to TiO2. Yellow 139, as I mentioned, orange 36, and 254. All three of them are probably the worst actors with respect to TiO2 and weathering. So when we reformulate that particular color, we're still able to use the 139 and orange 36, but now without the TiO2 in there, bringing in the brown 24 and the yellow 119, we're able to get that space, get the hiding, and then also get the weatherability. And so here's some early weathering, accelerated weathering data that we have for those two colors, which already starts to see some differences between the two types of formulation with respect to weathering. The fifth example is also a weathering related, but this is in particular regions where there is high acid rain content in there. So there's a test that is used to simulate acid rain resistance. It's called a fuming nitric acid test. And these are intended to test pigments that so that they would have a that longer term durability property. The test uses a 50-50 ratio of TiO2 for the test itself. One of the worst actors is the blues, the CPC blues, and this is all blues. So this particular example is a number of pigments in the pigment blue 15-1 alpha category. Again, this is the 50-50 TiO2 blend, and we can see delta E's after this test in the 20s areas, which is obviously not good for exposure to acid rain conditions. Thus, that brings in the pigment blue 28 to be able to help this property. And what we see here is the TiO2, as we know in regular weathering applications, it acts as a catalyst to be able to break down the organic pigment. In this particular case, in normal quote unquote weathering data, CPC blues are fine for weathering applications. It's when these acid rain environments are introduced, then the TiO2 begins to act as a catalyst in this type of chemistry as well. In coatings, we see a significant impact with this when we switch out the TiO2 for a blue 28 in there, so that there's some additional help there with respect to the exposure. Just some physical examples here and a color space visual for everybody here. On the coating side, when we reduce it by nearly 50% of the exposure, and then also you can see where the color spaces of these mixtures fall. Always the pigment blue 28 by itself is perfectly fine in this type of exposure, but it is more red than anything else. So there's always some help in that particular property by utilizing the pigment blue 28 versus the TiO2. On plastics, there's also help here. Although here we start to see differences between pigment blue 15-1 and 15-3. We do see about 50% improvement in the 15-1 space. However, we don't see much improvement in the 15-3 space, and that's because in the modification, the polymorphism of the particular crystals, the crystals are further apart in the 15-3 space, so the edges of those crystals are more exposed to the acid rain than the 15-1, which are almost on top of each other. So there's less exposure to the acid rain situation. And that's it. So next up, next month, it's a very general topic. I thought it would be really good to take a look at the blue color space. And there's a lot of options in those areas, and a lot you can do with blue. And so I will focus it on the types of options that are available in here. Of course, that'll be the last Tuesday of the month of July. And so you'll see that coming up soon. And then I'd like to open it up for any questions that we might have.